In mathematics, tetration is the next hyperoperation after exponentiation, and is defined as iterated exponentiation. The word was coined by Reuben Louis Goodstein, from tetra and iteration. Tetration is used for the notation of very large numbers. Shown here are the first four hyperoperations, with tetration as the fourth. Addition n copies of 1 added to a. Multiplication n copies of a combined by addition. Exponentiation n copies of a combined by multiplication. Tetration n copies of a combined by exponentiation, right to left. The above example is read as the nth tetration of a. Each operation is defined by iterating the previous one. Tetration is neither an elementary function nor an elementary recursive function. Here, succession is the most basic operation, addition is a primary operation, though for natural numbers it can be thought of as a chained succession of n successes of a. Multiplication can be thought of as a chained multiplication involving n numbers a. Analogously, tetration. Definition. For any positive real and non-negative integer, we define by iterated powers versus iterated exponentials. As we can see from the definition, when evaluating tetration expressed as an exponentiation tower, the exponentiation is done at the deepest level first. For example, note that exponentiation is not associative, so evaluating the expression in the other order will lead to a different answer. Thus, the exponential towers must be evaluated from top to bottom. Computer programmers refer to this choice as right associative. When a and 10 are co-prime, we can compute the last m decimal digits of using Euler's theorem. Terminology. There are many terms for tetration, each of which has some logic behind it, but some have not become commonly used for one reason or another. Here is a comparison of each term with its rationale and counter-rationale. The term tetration, introduced by Goodstein in his 1947 paper Transfinite Ordinals in Recursive Number Theory, has gained dominance. It was also popularized in Rudy Rucker's Infinity and the Mind. The term superexponentiation was published by Brommer in his paper Superexponentiation in 1987. It was used earlier by Ed Nelson in his book Predicative Arithmetic, Princeton University Press, 1986. The term hyperpower is a natural combination of hyper and power, which aptly describes tetration. The problem lies in the meaning of hyper with respect to the hyperoperation sequence. When considering hyperoperations, the term hyper refers to all ranks, and the term super refers to rank 4, or tetration. So under these considerations hyperpower is misleading, since it is only referring to tetration. The term power tower is occasionally used, in the form, the power tower of order n, 4. This is a misnomer, however, because tetration cannot be expressed with iterated power functions, since it is an iterated exponential function, owing in part to some shared terminology and similar notational symbolism. Tetration is often confused with closely related functions and expressions. Here are a few related terms. In the first two expressions a is the base, and the number of times a appears is the height. In the third expression, n is the height, but each of the bases is different. Care must be taken when referring to iterated exponentials, as it is common to call expressions of this form iterated exponentiation, which is ambiguous, as this can either mean iterated powers or iterated exponentials. Notation. There are many different notation styles that can be used to express tetration. One notation above uses iterated exponential notation. In general, this is defined as follows. With n, a, s. There are not as many notations for iterated exponentials, but here are a few examples. In the following table, most values are too large to write in scientific notation. So iterated exponential notation is employed to express them in base 10. The values containing a decimal point are approximate extensions. Tetration can be extended to define in other domains as well. Extension of domain for bases. Extension to base 0. The exponential is not consistently defined. Thus, the tetrations are not clearly defined by the formula given earlier. However, is well defined, and exists. Thus we could consistently define. This is equivalent to defining under this extension, so the rule from the original definition still holds. Extension to complex bases. Since complex numbers can be raised to powers, tetration can be applied to bases of the form where, for example, where tetration is achieved by using the principal branch of the natural logarithm, and using Euler's formula we get the relation. This suggests a recursive definition for given any. The following approximate values can be derived. Solving the inverse relation as in the previous section, yields the expected n, with negative values of n giving infinite results on the imaginary axis. Plotted in the complex plane, the entire sequence spirals to the limit, which could be interpreted as the value where n is infinite. Such tetration sequences have been studied since the time of Euler but are poorly understood due to their chaotic behavior. Most published research historically has focused on the convergence of the infinitely iterated exponential function. Current research has greatly benefited by the advent of powerful computers with fractal and symbolic mathematics software. Much of what is known about tetration comes from general knowledge of complex dynamics and specific research of the exponential map. Extensions of the domain for heights. Extension to infinite heights. Tetration can be extended to infinite heights. This is because for bases within a certain interval, tetration converges to a finite value as the height tends to infinity. For example, converges to 2, and can therefore be said to be equal to 2. The trend towards 2 can be seen by evaluating a small finite tower. In general, the infinitely iterated exponential, defined as the limit of as on goes to infinity, converges for e minus ex e1, e, roughly the interval from 0.066 to 1.44, a result shown by Leonhard Euler. The limit, should it exist, is a positive real solution of the equation y equals xy. Thus, x equals y1, y. The limit defining the infinite tetration of x fails to converge for x greater than e1, e because the maximum of y1, y is e1, e. This may be extended to complex numbers z with the definition, where w represents Lambert's w function. As the limit y equals infinity x must satisfy xy equals y, we see that xy equals infinity x is the inverse function of yx equals y1, y. Extension to negative heights. In order to preserve the original rule, for negative values of we must use the recursive relation. Thus, however, smaller negative values cannot be well defined in this way because which is not well defined. Note further that for any definition of is consistent with the rule because for any extension to real heights at this time there is no commonly accepted solution to the general problem of extending tetration to the real or complex values of. Various approaches are mentioned below. In general, the problem is finding, for any real or greater than 0, a super-exponential function over real x greater than -2 that satisfies a fourth requirement that is usually one of a continuity requirement, a differentiability requirement, a regularity requirement that, for all the fourth requirement differs from author to author, and between approaches. There are two main approaches to extending tetration to real heights. One is based on the regularity requirement, and one is based on the differentiability requirement. These two approaches seem to be so different that they may not be reconciled, as they produce results inconsistent with each other. When is defined for an interval of length 1, the whole function easily follows for all x greater than -2. Linear approximation for the extension to real heights. A linear approximation is given by, hence, and so on. However, it is only piecewise differentiable. At integer values of x the derivative is multiplied by. Examples. A main theorem in Huysmans' paper states, let if is continuous and satisfies the conditions, is differentiable on, is a non-decreasing or non-increasing function on, then is uniquely determined through the equation where denotes the fractional part of x and is the iterated function of the function. The proof is that the second through fourth conditions trivially imply that f is a linear function on -1, 0. The linear approximation to natural tetration function is continuously differentiable, but its second derivative does not exist at integer values of its argument. Hushman derived another uniqueness theorem for it which states, if is a continuous function that satisfies, is convex on, then, here is Hushman's name for the linear approximation to the natural tetration function. The proof is much the same as before. The recursion equation ensures that, and then the convexity condition implies that is linear on. Therefore the linear approximation to natural tetration is the only solution of the equation and which is convex on. All other sufficiently differentiable solutions must have an inflection point on the interval. Higher order approximations for the extension to real heights. A quadratic approximation is given by, which is differentiable for all, but not twice differentiable, if this is the same as the linear approximation. Note that this function does not satisfy condition that tetration cancels out, because it is calculated top-down, namely, a cubic approximation, and a method for generalizing to approximations of degree n are given at extension to complex heights. There is a conjecture that there exists a unique function f which is a solution of the equation f equals exp, and satisfies the additional conditions that f equals 1 and f approaches the fixed points of the logarithm as z approaches plus or minus I infinity, and that f is holomorphic in the whole complex z-plane, except the part of the real axis at z-2. This function is shown in the figure at right. The complex double precision approximation of this function is available online. The requirement of the tetration being holomorphic is important for its uniqueness. Many functions can be constructed as were in a real sequences which decay fast enough to provide the convergence of the series, at least at moderate values of. The function s satisfies the tetration equations s equals exp, s equals 1, and if alpha n and beta n approach 0 fast enough it will be analytic on a neighborhood of the positive real axis. However, if some elements of alpha or beta are not 0, then function s has multitudes of additional singularities and cut lines in the complex plane. Due to the exponential growth of sin and cos along the imaginary axis, the smaller the coefficients alpha and beta are, the further away these singularities are from the real axis. The extension of tetration into the complex plane is thus essential for the uniqueness. The real analytic tetration is not unique. Open questions. It is not known whether there is a positive integer n for which n pi or n is an integer. In particular, it is not known whether 4 pi is an integer. It is not known whether nq is an integer for any positive integer n and positive non-integer rational q. Particularly, it is not known whether the positive root of the equation 4x equals 2 is a rational number. Inverse relations. Exponentiation has two inverse relations, roots and logarithms. Analogously, the inverse relations of tetration are often called the superroot and the superlogarithm. Superroot. The superroot is the inverse relation of tetration with respect to the base. If, then y is an nth superroot of x. For example, so too is the fourth superroot of 65,536, and so 3 is the third superroot of 7,625,597,484,987. Square superroot. The second-order superroot, square superroot, or super square root has two equivalent notations, and it is the inverse of and can be represented with the Lambert W function. The function also illustrates the reflective nature of the root and logarithm functions, as the equation below only holds true when, like square roots, the square superroot of x may not have a single solution. Unlike square roots, determining the number of square superroots of x may be difficult. In general, if then x has two positive square superroots between 0 and 1, and if then x has one positive square superroot greater than 1. If x is positive and less than, it doesn't have any real square superroots. But the formula given above yields countably infinitely many complex ones for any finite x not equal to 1. The function has been used to determine the size of data clusters. Other superroots for each integer n greater than 2. The function nx is defined and increasing for ex1, and n1 equals 1, so that the nth superroot of x exists for ex1. However, if the linear approximation above is used, then if -1 less than y0, so cannot exist. Other superroots are expressible under the same basis used with normal roots. Supercube roots, the function that produces y when, can be expressed as, the fourth superroot can be expressed as, and it can therefore be said that the nth superroot is. Note that may not be uniquely defined, because there may be more than one nth root. For example, x has a single superroot if n is odd, and up to 2 if n is even. The superroot can be extended to, and this shows a link to the mathematical constant e, as it is only well defined if 1 exe. Note that and thus that. Therefore, when it is well defined, and thus it is an elementary function. For example, it follows from the Jalfond-Schneider theorem that superroot for any positive integer n is either integer or transcendental, and is either integer or irrational. But it is still an open question whether irrational superroots of transcendental in the latter case. Superlogarithm. Once a continuous increasing definition of tetration, xa, is selected, the corresponding superlogarithm slogar x is defined for all real numbers x, and are greater than 1. The function satisfies